All right, so welcome to Math317 Operations Research. What I want to do today is solution key exams here is talk about the Brouwer fixed point theorem, which says that any continuous function f from delta n to delta n has a fixed point. When you see this, of course, your first question should be either what is delta n or why do we care about this theorem? So since we are in the midst of pre-registration, I was trying to time things so that we would get to this lecture today, so we can talk a little bit about what would you do if you actually took a class in real analysis. So in a lot of the stuff that we're doing, we need to be able to make certain arguments rigorous. There's a couple of different ways we can come to the material. I've decided to do something a little bit more organic, and just as we're going, we will get stuck a few times, and that will kind of motivate the real analysis that we're going to do. What you have to remember is mathematics is not discovered in a vacuum. Usually there's some guiding question that people are interested in, and that inspires them to develop the methods, the techniques, the results. When I teach multivariable calculus, I often arrange for a trip to the library where they take out some of the rare books. We have one of the greatest collections, I think, in the world. Professor Pesikoff in astronomy has donated many of his items. And you can see, first edition of Newton, Kepler, Galileo, Copernicus. And a lot of the mathematics that was developed was motivated by real problems, trying to understand orbits of planets. And so what I want to do today is talk a little bit about trying to prove a fixed point theorem. And in the efforts to do so, we're going to see some results from real analysis that we're going to need. So we will eventually define what I mean by delta n. We'll eventually prove the Brouwer fixed point theorem using Sperner's lemma from yesterday. We'll concentrate in the case of 2 dimensions, but the more general case is not so bad. So this is a motivation for those of you who are trying to decide what you want to register for next semester to take real analysis if you haven't already done so, or applied real analysis, either one is fine. We want to start off with the most general situation possible. Now, frequently, the most general situation possible is not the easiest one to investigate. Why do we like triangles and rectangles? Minimum number of sides. What else? What's nice about triangles and rectangles? Know a lot about them. In what sense? What can we do with triangles and rectangles? So when we're doing integration, when we have to integrate, there are 2 difficulties, the integrand and the region of integration. So if I give you a circle, if I convert from Cartesian to polar, what does the circle look like in polar coordinates? Square. Not quite a square. Close. Square, the length and the width have to be the same. It's a rectangle. So in polar coordinates, a circle is just a rectangle. Maybe this is the radius direction, or I guess maybe no, I think we do maybe theta down here and the radius up here. What if I gave you a sphere in 3-dimensional space? What would that look like if we convert to spherical coordinates? Prism implies that it could be at an angle. It's a very special prism. So this is a multivariable calculus review. Rectangular prism or box, Amazon package, something like that. It'll look like something like this. So what do you have in a situation like this? Oops. I was trying to just get rid of the stuff on the bottom. So you would have, for instance, 0 less than equal to rho, less than equal to capital R, 0 less than equal to, now it depends if you're a physicist or a mathematician as to is theta coming down from the z-axis or is it phi coming down from the z-axis. In math classes, we want phi to be coming down from the z-axis so that we have theta for the xy plane. So it'd be 0 less than equal to phi less than equal to pi, and 0 less than equal to theta less than equal to 2 pi. So a sphere becomes a box in spherical coordinates. We know how to integrate over boxes really well. Everything is nice. We can chop it up into lots of smaller pieces, and then we can chop those up into smaller pieces if we need to and keep iterating. So these are wonderful shapes to work with. This is one of the big ideas in multivariable calculus, is take a complicated region and convert it to a simpler region. Now, when you do this, this is often going to change the integrand. If your integrand only depends on the distance from the origin, then frequently this is a wonderful thing to do because the theta and phi integration becomes trivial. You also, of course, have to figure out the change of variables formula. How much is dx, dy, dz in d rho, d phi, d theta space? And that's where you get the rho squared sine phi, d rho, d theta, d phi. All right, so what are we going to try to do? We want to try to prove that, let's say we have some function f from some space S to another space S, f is nice, then there exists an x in S such that f of x equals x. So we want to say that if we have a function that maps a space to itself, then there will be a fixed point. So is this true for any function that maps any set to itself? And if not, can you give me a counterexample? So can you give me an example of a function that might map some set to itself, but will not have a fixed point? And as a hint, the Bauer fixed point theorem says any continuous function from delta to delta has a fixed point. So if you had to guess, what would you guess would be true about your function? Discontinuous. Again, I haven't defined what delta n is, but given that one of the conditions is that the function is continuous, so can somebody give me a space and a discontinuous function so that f of x is never x? What should we take for our space? Okay, so you want the whole plane.
Yeah, so like R2.
Okay, so S equals R2, good. And f of x, y equals?
I mean, I would say like 1 over like x would work
Well,
as a discontinuous function, but
you got to be careful because if x equals 1, and we now have a point because you're mapping R2 to R2.
right.
But as soon as you're using the whole infinite, there's a nice function that you can use. In fact, your function can even be continuous. So give me a function that won't have a fixed point on R2.
So, like an empty function.
Well, you've got to tell me what it maps x, y to. And you just want to choose it so that you will never have f of x, y equal x, y. Yeah, x plus 1, y plus 1. I was actually thinking of that as well. There's no need to do y plus 1. As soon as you add 1 to x, that's enough. So again, whenever you're proving a theorem, one of my professors, Professor Jones, was really good about this. Remove a condition and show why it's not true. So what we're seeing here is, hey, we could actually have a continuous function that doesn't have a fixed point. And the issue here is that the set S is infinite. Infinite in what way? Not infinite in having infinitely many points, but unbounded. So the issue is S is unbounded. And so because S was unbounded, we could just translate everything. All right, so let's take now maybe S to be the interval 0, 1. Can somebody give me a function on 0, 1 that does not have a fixed point? So what must be true about this function? Or what is likely true about this function? Likely that this one is going to be discontinuous, right? And again, I haven't defined what delta n is, but the condition there was the function is continuous, there's a fixed point. Here, the function is continuous, but the region is unbounded. So maybe delta n has to be some kind of bounded set. So since it's discontinuous, I'm going to assume I can write it like this. Let's have two different definitions. Let's have it for one. It's going to be defined this way: 0 less than equal to x less than equal to 1/2, and then 1/2 strictly less than x less than equal to 1. So can somebody give me a choice for the function where we won't have a fixed point?
Does it have to map to something in the set?
Yes, the function is from S to S. Because the whole point is the fixed point is in the space. There's some point where when you apply f, you stay where you started. So almost anything is going to work. How should we define f on the first half of the interval? How should we define it on the second half?
1/1 plus x.
You're making it too hard. Be nice to me. The function doesn't have to be continuous. Just give me a definition. What should the function be on the first half of the interval to make sure there's no fixed points on the first half of the interval?
X plus 1/2.
You could do x plus 1/2.
1 minus 1/2, or 1 minus x.
So if you do 1 minus x when x equals 1/2, it would be 1/2. Give me something, as soon as you give me something involving x, I have to do a little bit of algebra to make sure that there's no fixed point. Give me something really easy so I can just look at this and see there's no fixed point. 1, right? If you define it to be 1 on the interval from 0 to 1/2, clearly there's no fixed point in the first half of the interval. What should we define it to be in the second half of the interval? 0, right? We don't have to use 1 and 0. I could have used 3/4, but just choose something really straightforward. Whenever you're doing examples like this, try to come up with the simplest example you can think of. If you start doing things such as, x plus 1/2, that will work. That will not have a fixed point. And it's not so bad because if it was a fixed point, you would need x plus 1/2 to equal x. So that means 1/2 would have to be 0. But you're still doing a little bit of a calculation. If you just make it 1 and 0, it's clear that it can't be a fixed point. All right, so this tells us that we need at least some conditions on the set, and we need some conditions on the function if there's going to be a fixed point. The next thing is trying to decide what we want to study. And so the various things are going to be, we could have an interval, we could have a triangle, we could have a tetrahedron, and then I hope you can understand that it's supposed to be a tetrahedron, and so on and so on and so on. These are going to be the regions we're going to study. When I'm drawing my triangles, I could draw lots of different types of triangles. I could draw an equilateral triangle, I could draw a right triangle, I could draw other types of triangles. What kind of triangle do you think would be the nicest to draw? Equilateral. And if it couldn't be an equilateral, what would you do as your second choice?
Right.
Which right triangle? Isosceles right triangle, right? If I couldn't do equilateral, I would probably do isosceles right. And again, one of the things that's nice about a lot of these is if I give you an equilateral triangle, and we've seen this before, I can then subdivide this very nicely. And then I can subdivide all of these very nicely. And so on and so on and so on. So in terms of breaking the region up into smaller subregions to understand, very simple, very straightforward with an equilateral triangle. Each region is going to be a nice smaller copy, same orientation, or after rotation and whatnot as the original. Okay. So the next result I want to do is I want to do some kind of reduction argument. And this is extremely common in analysis. And so the idea is the following. If no for S and nice functions on S, and t is nicely related to s, know for t and nice functions on t. So the idea here is, imagine I can prove that if I have a set S and I have nice functions on S, then these functions have a fixed point. And I have another set T that is related in a very nice way to S. I would like to then be able to say, since I know the result holds for S, I can transfer the knowledge to T, and it's sufficient to study S. So my favorite logarithm is the W log. Does anybody know what the W log is? Without loss of generality, right? Without loss of generality, it's enough to consider left-handed people, right? And you show that the argument holds in this case. So let's say we have some region T, and we're going to consider maps from T to T. Let's call these maps, G from T to T. And we have some region here, S, and we can consider maps F from S to S. And let's assume we have some function phi and phi inverse that map us from T to S or from S to T. Okay, so hopefully you've seen this before. I want phi to be a bijection. That means it's one-to-one, also known as injective, and it's onto, surjective. So what does this mean? It means injective, or the one-to-one, phi of x equals phi of y implies x equals y. Could I say if and only if? So normally we say it's injective if phi of x equals phi of y implies x equals y. That the only way 2 points can go to the same point is if they're the same point. What about the other direction? If x equals y, does phi of x equal phi of y?
Not necessarily.
So if x equals y, will phi of x equal phi of y? So if x and y are the same point, if I apply phi to them, will it be the same? Yeah, why? Well, no, but I'm saying if I assume x and y are the same, will phi of x have to equal phi of y? Yes, why? They're the same point. If x equals y, then phi of x has to be phi of y because x is the same as y. I can just substitute y for x. This is really an if and only if. But one direction is so straightforward. Well, if x equals y, of course phi of x equals phi of y. That's not really that surprising or exciting. The content is the fact that if phi of x equals phi of y, then x equals y. So I give you, phi of x equals x squared. Is this one-to-one? Can you give me 2 points that map to the same point that are not the same? -1 and 1 map to 1, so not one-to-one. It is one-to-one on the interval 0, infinity. So depending on where your function is defined, it may or may not be one-to-one. So the second one, the onto, means for all S in S, there exists a T in T such that phi of T, that's a terrible T, phi of T equals S. So it's onto if every point is hit, is you give me some point S, and I can find some point here that's mapped to it. And because the function is one-to-one and onto, it turns out its inverse exists, and its inverse is also one-to-one and onto. So phi allows me to map something from T to S Phi inverse allows me to map something from S to T. Okay? And the whole idea is that if we have such functions, then we can often push knowledge from one setting to another. Now, as an one of the most beautiful classes, this is not an opinion, this is just a fact. One of the most beautiful classes in all mathematics is complex analysis. And one of the results is if omega is a simply connected region in the plane that is not all of C, then there exists a infinitely differentiable complex bijection from omega to the open disk D. So in other words, if I give you, some nice set like this, I give you the unit disk here, I can find a map phi. And in many cases, you can actually extend the map phi to the boundary. So I remember when I was taking a class in mathematical physics, I had something like this, the pentagram, and was told to actually do the formula explicitly and calculate the closed form expression to map the pentagram to the unit disk. This is the only problem I refused to do in my undergraduate career. I was getting enough of the homework problems right in the class that it just wasn't worth going through and doing the detailed calculations. Everybody, at some point in your life, you have to prioritize how much is something worth. There is an explicit formula that allows you to do this. Absolutely wonderful and amazing that you can write down in closed form. And this is a question that has been asked before. How explicit can we make some of these calculations? If there's a fixed point, can we find it? In a situation like that, not only can we often say that there is a map from one to another, we can even write down exactly what it is. So in complex analysis, you learn how to do this. Okay, absolutely amazing that such things exist. The unit disk is very nice. The unit square is nice. The equilateral triangle is nice. What this is saying is all of these shapes are equivalent, and we can find a continuous function from one to another. Let's define f of s to be the set of all functions f such that f from s to s has a fixed point, and say f is continuous. Okay, so it's the set of all functions that have a fixed point. Can somebody give me an example of an element of this set, a function from S to itself that's continuous, that has a fixed point? Can we at least prove that this set is never empty? What function could we use? Yeah, good, the identity function. Is always an example. So we're at least not studying an empty set. So now let's go back to what we had a moment ago. So we had our stuff over here. Oops. So here's our setting. We have our functions on T, we have our functions on S. And we have a map from one to the other. Okay, so let's imagine we have a function on G. Can we associate to that function something on S? So let's look at, so G goes from T to T. So if we look at G, and then let's start off with phi inverse. And then let's end with phi. where does this take input and where does this take output? So if we look at phi composed with g composed with phi inverse, where is the input? Where does the input live? It lives in S. And when we apply phi inverse that takes something in S and gives us something in T, we can now apply G, and that gives us back something in T. And then we apply phi, and that gives us something in S. So this is going to be a map from S to S. Okay. So if I give you a function G, I can come up with an associated function. What should we call this associated function? Maybe call it f sub g to remind ourselves that it depends on g. Or if you want, you could call it maybe f sub phi comma g. But if we fix the phi that we're using, there's no need maybe to keep writing it. But you know, f of g or f sub phi g would both be good names. All right, so imagine, you know, assume every continuous function f from S to S has a fixed point. If we let f sub g be phi composed with g composed with phi inverse, it's easy to see this is continuous if phi and g are continuous. So because this is a continuous function from S to S, what do we know about this function? Has a fixed point. So let x star be the fixed point. So fg of x star is just x star. Or phi composed with g composed with phi inverse of x star equals x star. Okay. All we have to do now is just unwind what this means. This means phi of g of phi inverse of x star, 1, 2, 3 parentheses, is x star. What should I do to both sides? So I've got phi of g of phi inverse of x star is x star. What am I trying to find? So you should always know what is the objective. What are we trying to prove right here? We started off with f has a fixed point. What are we trying to show? Good, we're trying to show g has a fixed point. Trying to show g has a fixed point. Right? We know that any function f by assumption that's continuous has a fixed point on S. We want to show any function g that's continuous on this related space T has a fixed point. What is the candidate? What do you think the candidate point is going to be for the fixed point of g? When you look at this, what do you think the candidate's going to be? Phi inverse of x star. I want to get a phi inverse of x star. How could I get a phi inverse of x star? Yeah, by what? So what do I apply to both sides? I've got phi of g phi inverse x star equals x star. What should I apply to both sides? Phi inverse. So apply phi inverse. So we get phi inverse of phi. I must really love you guys to write all this detail of x star, 1 parenthesis, 2 parentheses, 3 parentheses, 4 parentheses equals phi inverse of x star. But what is phi of phi inverse? 1. So this yields g of phi inverse of x star is phi inverse of x star. This is our fixed point. So the whole point of this is if there's one space you can understand, you can reduce everything to that. This is the principle of the hammer. If all you have is a hammer, everything looks like reduce to what you know. So if there's one space that I can study in great detail, then any space that is connected to that is going to be the same. And I will have a fixed point result there as well. So the original statement is that any continuous function, essentially from the line segment to the line segment, the triangle to the triangle, the tetrahedron to the tetrahedron, and so on and so on and so on, will have a fixed point. But when we prove this, we're proving it from far more than just a triangle or whatnot. We're proving it also for circles, for boxes, for any nice regions, so long as we can continuously map from one to the other. Now, if I take the annulus, a circle with the center punched out, I may not be able to map that. So that would take maybe some more thought to see, do I have something in that case? And so you have to be careful as to how far do you push things. So for example, let's let D be the set of all xy, x squared plus y squared is less than or equal to 1. I'll do the closed disk. And I'll let d bar minus 0, 0 be d bar minus the origin. So I can clearly give you a map from the punctured disk to the disk. What would be a nice map that would map the punctured disk into the disk? Can somebody give me a map that would map the punctured disk into the disk? The identity. I could take the identity. Can I take the identity back? I can't. So the problem is, if I use the identity, it's not surjective, it's not onto. So note, the identity is not onto.
On the way back.
On the way into.
Oh, because nothing gets hit in the middle.
Nothing gets hit in the middle. So can you give me, so in the interest of time, I'll just say, if I give you f of r e to the I theta is f of r e to the I theta plus, say, pi halves, no fixed point. I just rotate everything by 90 degrees. So imagine you have a record and you spin it right round 90 degrees. Will any point stay where it was? The center. Will any other point other than, so if I remove the center, then, so this is an example that it's not enough to just have a bounded region and a continuous function. So I have a nice continuous function on this bounded region. It's not going to have a fixed point. So as much as possible, when you're trying to get a feel of theorems, play with them. Try to come up with lots of different cases. Analysis is one of the hardest classes, I think, in mathematics because there are so many possible counterexamples. My professor of analysis, Professor Jones, always told us, remove one of the conditions from the theorem. The theorem should now either be false or it should be much harder to prove. And that's a great way to try to get a sense of what's going on. And so, again, when we're trying to get a sense, we can prove that if two regions are related by a bijection, then if one has fixed points, then the other one has fixed points for their continuous functions. If I give you a punctured disk, what we now know is they can't be related by a bijection. So this will be a proof that there is no bijection between the punctured disk and the whole disk, because if there were, then I'd be able to get a fixed point, and I can't here. So this is a nice way of proving that you can't do something. All right. Prove things. So what we're going to do is the following. We're going to use barycentric coordinates. And so here is my V0, my V1, my V2. This is going to be the point 1, 0, 0. This is 0, 1, 0. And this is 0, 0, 1. And then any point over here is going to be, I'll do it as, S, T, 1 minus S minus T. So 0 less than equal to ST less than equal to 1, and S plus T is going to be less than equal to 1. So I'm writing my point as a triple. I could also write it as x0, x1, x2, with 0 less than equal to xi less than equal to 1, x0 plus x1 plus x2 equals 1. Lots of different ways of writing it. Okay. We're now going to define we have some function, we'll call this, delta 2. So we're going to define some function from delta 2 to delta 2 to be continuous. Does it have a fixed point? So if I give you some point, f of x naught, x1, x2 would be some new point, x naught prime, x1 prime, x2 prime. It takes some point and it maps it to another point. Is it possible, can x naught be greater than x1, x0 prime, x1 greater than x1 prime, x2 greater than x2 prime? Is that possible? Can all of this hold? So is it possible that if you look at your initial point, each coordinate is larger? Why not? Why will it be outside the triangle?
Why?
Yes.
Oh, because if you had the point 0, 1, 0, and you added something a half to each of those coordinates, you'd be exceeding for s plus t is less than equal to 1.
Okay, I think the cleaner way to say this is if we sum, this is x naught plus x1 plus x2 would be strictly greater than x naught prime plus x1 prime plus x2 prime, and both of these are supposed to equal 1. And so it wouldn't be in the triangle. So it can't be the case that when you have the map, that your initial coordinate is always strictly greater. So when we look at f of some point x naught, x1, x2 equals x naught prime, x1 prime, x2 prime, at least one I has xi prime less than or equal to xi. Or do you want to do it the other way? Right, they can't all be, okay, so, all right. I guess the way I'm doing it over here is, I think I need to do it this way. At least one of them has to be greater than or equal to the previous, right? What if all are equal? What would be true? That's a fixed point. So similarly, at least one I has xi prime less than or equal to xi. It's the exact same argument. right? Just flip which side you want to look on. So what we're going to do is we're going to define a new function, the index function. So the index function of a point x0, x1, x2 is the first I such that xi prime is strictly less than xi. Okay. Always exists if no fixed point. Okay. So if there's a fixed point, then of course there won't be any index where it's strictly less than. But if we're trying to show that a fixed point exists, if we have a fixed point, then we have nothing left to do. So the only thing we have to worry about is imagine there's a situation where we don't have a fixed point. We're going to try to deduce a contradiction. And from this, we need to define a new function, the index function. It's the first index where your output is less than your input. So let's look a little bit. So we have our triangle. And it has 3 points initially. 1, 0, 0, 0, 1, 0, 0, 0, 1. Assume f has no fixed point. So index is always defined. What can you tell me about the index value here? So what must be true about the index value at the point 1, 0, 0? What's the first place where I don't agree with 1, 0, 0? So I have f of 1, 0, 0 is some point, let's call it A0, A1, A2. What's the first place where A0, A1, A2 disagrees with 1, 0, 0? The first place where it has a smaller value. Which component? The 0th component, the first component, or the second component? I'm sorry? 0. Because if the 0th component, it can't be larger than 1. If the 0th component was a 1, then what would A1 and A2 both have to be? They'd have to be 0 because the sum of the entries is 0. So we would have to label this, the index value would be 0. When we look at here and we apply f, what's the first place where f is going to disagree and be smaller? Can't be the 0th component. You can't be smaller than 0. If it happened to equal 1, then this would be our fixed point, because then the next one would have to be 0. So we have to label this 1. And in a Shaka, what do you think we label the top? 2. So now let's look at what goes on down on the bottom. The points here are going to be of the form x0, x1, and 0. What must be true about the first component where this is going to be smaller than x0, x1, 0? What are the only possibilities on the bottom for the place where we have the first component that's 0, that's not the same, but is actually strictly smaller? Could it be the third? Could it be the final component, the second component? Could that be the first component where it's smaller? No, because that's a 0. So the index has to be labeled what? 0 or 1 down here. Over here on the next one, we now have the points 0, x1, x2, right? You're not going to be smaller in the 0th component. So what are the labels on this wall? 1 or 2. And then for the last one, it's going to be of the form x0, 0, x2. What are the labels going to be? Does this look familiar? We now have a triangle where on the boundary, we have 0, 1, 2 as the 3 vertices. The bottom side, everything gets a 0 or 1. And then the other 2 sides, it's a 1 or a 2, it's a 0 or 2. This is the same situation as Sperner's lemma. So what is going to happen is that if we now take our triangle and we subdivide, there has to be a triangle that has a 0, 1, 2 labeling, right? And then maybe it's this one. And let's say the labeling is 2, 1, 0. So by Sperner's algorithm, there has to be something. And the goal is to show that as we take smaller and smaller triangles, if you have labelings that are 0, 1, 2, as they get closer and closer and closer, that's going to be a contradiction. Because you're saying, I differ in coming in this direction, I'm going to differ in the 0th component. In this direction, I'm going to differ from the first component. In this direction, I'm going to differ from the second component. But by continuity, it's going to be the same. So we'll see in the next lecture that this is going to be a problem. What you would love to do is to take this triangle and then subdivide this triangle, right? And say, we know that there's a 0, 1, 2 triangle here. Let's then subdivide that and then say that there would have to be a 0, 1, 2 triangle in there. Why can't we do that? Why can't we apply Sperner's lemma to this smaller triangle?
You don't know if the like edges.
Right, because we don't know that the edges are true. So you can't subdivide like this. Cannot subdivide. Sperner is unavailable. So we can't just say, we know there's a triangle which is 0, 1, 2. Let's have that be where our action is, and then we'll divide that, and then we'll divide that, and then we'll divide that, and then we'll divide that. What we're going to have to do is we're going to always have to go back to the original triangle and divide it into smaller and smaller pieces. And then we're going to have, unfortunately, this nightmare of like scintillations on a screen of smaller and smaller triangles flashing on where something happens. And then what we're going to have to show is that when you have this sequence of triangles flashing all over the place, those sequences of triangles have to have a subsequence that converges. And so even though they don't have to be inside each other, there's going to be a sequence of these triangles that will be converging to a point. And this is where we're going to start to see some results from analysis. So again, there's 2 ways you can do this lecture. I think in previous years, I started off by doing the analysis and then proving the fixed point theorem. Today, I decided, let's try to prove the fixed point theorem and then reach a point where we get stuck. And now we have to develop some analysis. And the problem is, we'd love to just keep subdividing and stay in the range where we know something is happening, but we don't know that Sperner is available. And because of that, we now have to go back and to the original triangle and divide that into smaller pieces, and then we get something. And then divide the original triangle into even smaller pieces, and we get something. And we need to show some kind of convergence there. All right, so this is hopefully giving you a sense of how we have to be careful in a lot of these arguments. We will see on Monday how to do this carefully. There will be no class on Friday. I'm working to get a video for you to watch from some local businesses. All right, I'm going to stop recording here.